Since the Cambrian explosion 520 million years ago, creatures such as Diana cactiformis, or the walking cactus, have developed external exoskeletons to protect them from the concurrent rise in predation at the time. Arthropods quickly followed suit, securing their place as the most abundant animal group on the planet. Approximately 520 million years later, in 1847, Sir Richard Owen coined the term exoskeleton to describe the external covering of invertebrates for support and protection. Unfortunately, for larger creatures, muscle strength doesn't scale proportionately with size. And because the relative weight of an exoskeleton is much greater than that of an endoskeleton comparative to a creature's size, at a certain size, exoskeletons become too heavy for a creature to move efficiently, and therefore rarely survive the process of natural selection in animals larger than the crab. Except in the case of Arthropleura, but luckily for us they've been extinct for 290 million years, so we never have to think about them again. Because of this scaling inefficiency, it took a few decades after Sir Owen's popularization of this concept for the first exoskeleton designs to find their way into the patent office, where the best of capitalism's technological progress can be found. The year is 1890. Alice Sanger has just become the first female staffer in the White House. 24 tornadoes appear in Mississippi, killing over 146 people, and the Sleeping Beauty Ballet is premiering at the Imperial Mariinsky Theatre in St. Petersburg. Just down the road, a young inventor by the name of Nicholas Jahn has just patented the first recorded design of an exoskeleton, a lower limb exercising apparatus employing a leaf spring operating in parallel to the legs to augment the operator's ability to run faster and jump higher. In a sense, Jahn had attached an archery bow to each leg. Though initially unpowered, Jahn's designs marked the first foray into technical augmentation of human abilities, and a later patent in the same year saw compressed gas bags to store the energy attached to the back, filling as the foot falls, creating pressure in the bag, then said pressure being released as the operator lifts their foot from the ground. 27 years later, in 1917, Leslie C. Kelly patented her improvement on the pedometer, or walking machine. The proposed design provided relief to muscles during running using a small steam engine worn on the operator's back. The artificial limbs worked in parallel with the human's limbs, like Jahn's apparatus, but were directly connected to the power source. However, this design was never released, and it would take another 40 years for an update to be released in this emerging field. In Schenectady, New York, 1946, the Atomic Energy Commission and the United States Air Force began their joint AEC-USAF nuclear propulsion program to determine the feasibility of nuclear energy for the propulsion of aircrafts. Unfortunately, at the time, nuclear reactors ranged from the size of a truck to the size of a large truck, and so the General Electric Company, or GE, was hired to take these experimental designs and make them a reality in the form of a modified Convair B-36 Peacemaker, a high-tech strategic bomber, chosen for its abnormally long wingspan, clocking in at 230 feet, or 70 meters. During these atomic experiments, General Electric were burning through their government-issued super soldiers to lift their nuclear equipment, so they began development on a tool that would allow the engineers to handle heavy and potentially volatile equipment with greatly amplified strength without sacrificing their dexterity. GE called these new tools CAMs, or Cybernetic Anthropomorphous Machines. But after 12 years of development, they always ended up too clumsy and inefficient for practical use. Enter Ralph S. Mosher, General Electric lead engineer and the father of powered exoskeletons. To this partial failure, Mosher said,
"I realized that after a certain point, improvements in mechanical dexterity added little to a manipulator's performance, so I began wondering why a human being is so efficient and a slave robot so awkward. Soon it was obvious that the manipulator's operator was missing what he ordinarily experiences, a sense of feel.
And with further funding of the AEC-USAF nuclear propulsion program, Mosher revealed the Handyman, a pair of claw-tipped robotic arms hooked around the operator's shoulders. The Handyman met all the requirements General Electric wanted from their cams: strong enough to crush golf balls, sensitive enough to pack eggs, and dexterous enough to light matches. Despite this incredible advancement, the Handyman had its drawbacks. The force feedback electronics were bulky and complex, with heavy robotics attached to both external machinery and the operator's back. The servos and racks were highly specialized and inordinately expensive, unable to be produced to any noticeable scale. These drawbacks and the current technology prevented any feasible or realistic plans for continued development. The US military. Best known for their rambunctious attitude, tactical military operations and impressive budget, this organization has a history of unique expenditures, consistently attempting to blur the line between reality and science fiction in the name of security and defense. One such foray into the future was their continued funding of General Electric's, with Mr. Mosher at the lead, who too was discovering his passion for expanding the limits of human capabilities. Starting in 1965, Mosher began his work on the Handyman's successor, the Human Augmentation Research and Development Investigation Man, shortened to the Hardyman. During the first year of research, Mosher focused on human factors to provide machinery with human-like action that mimics an operator's natural motion. The original design incorporated an internal exoskeleton to record movement attached to the operator, and an external exoskeleton to recreate the operator's movement. To achieve this, each internal exoskeleton joint had a duplicate on the external exoskeleton, geometrically superposed so that the corresponding joint axes are approximately collinear. To reduce forces experienced by the operator, the Hardyman used large bilateral servos reflecting the movement of the operator onto the external exoskeleton, and reflecting the working forces back onto the operator reduced by a factor of 25, so the operator can sense the forces on the machine as it's working. The design possesses no complex controllers, a large issue with the Handyman, or exposed limbs, as the operator stands inside the structure, surrounded and protected by it. It was after this first year it became clear to Mosher that the arm and leg systems must be split up due to the
practical considerations related to the build-up and compliance of servo systems.
Problems with these servo systems continued, as GE had
not yet succeeded in developing a complete hydromechanical servo system to the point where it could handle the exoskeleton's requirements.
Because of these issues, the Office of Naval Research, who is also involved somehow, directed the program to focus on the arm systems, as it involved lower risk, and Mosher recognized that a demonstration of its success was essential to continued support of the program, and by the end of 1969, they were finally complete. Following this success, in the late 70s, the leg system was almost finished, and although initial tests were encouraging, funding was running out, so the final product was presented, which
achieved limited success in walking. The machine responds to the man's motion, but the operator could not balance or walk without external support.
In his paper on the project, titled Handyman to Hardyman, Mosher stated,
"In spite of these achievements and the expectation for continued progress, the difficulties of duplicating many feats of the human brain and nervous system still remain formidable. Consequently, many mechanical operations will not be automated for some time."
He then went on to identify 4 key factors to be considered when designing powered exoskeleton systems. Number 1. Equipment must be practical in terms of size, cost, reliability, and ruggedness. Number 2. Power and control components must suit the particular system application. 3. Good force and position sensors must be incorporated. And 4. Mechanical arm kinematics must be appropriate and adequate. Although these factors are fairly broad, they set effective base rules for the design and production of exoskeletal systems, still followed to this day. Later in the paper, common usage of these cams were described as being for military use, bomb handling and heavy loads, and Mosher unveiled a bonus cam in the form of the
walking machine,
standing 10 feet high, 12 feet long and 3.5 feet wide, these quadruped monstrosities would travel at 5 miles per hour and carry 500 pounds of load, with the front 2 legs controlled by the operator's arms and the back 2 controlled by their legs. To clarify his sanity, Mosher went on to say,
"In order to keep things in proper perspective, it must be pointed out that the walking machine is not viewed as the future means of land transportation."
And then inexplicably he goes on to say,
"It can most certainly compete with helicopters in cargo transport roles that require movement independent of weather conditions over extremely rough terrain,"
touting its ability to be piloted without expensive training and its relatively modest production costs. Mosher continued to predict that in the future, the Hardyman's operator will react in such a natural manner that he subconsciously considers the machine as part of himself. He continues, "It is conceivable that a 20 or even 50-foot tall Hardyman can be built with the operator inside as the brain or controller, with force and position information being scaled down accordingly, which is wild." Though the Hardyman wasn't entirely successful in the form of a fully functional, powered exoskeleton capable of remote operation as was initially intended, it was proven as a viable solution to operating in extreme environments, bomb loading, material handling and cargo transportation over rough terrain, which Mosher believed would be realized in some form in the near future. Across the world in what was once Yugoslavia, at the Mikhailo Pupin Institute, Miomir Vukobratovic began work on his kinematic walker. Featuring a hydraulic actuator to drive hip and knee movement, the initial design quickly evolved into the partial active exoskeleton, switching to pneumatic actuators to control movement of the hip, knee and ankle, as well as abduction and adduction at the hip for greater frontal plane stability. The design was then further modified into the complete exoskeleton by extending the torso attachment to enclose the entire chest of the operator. At this stage, more than 100 clinical trials were performed with this device, resulting in a number of patients with varying degrees of paralysis mastering the ability to walk using the complete kinematic walker with the help of crutches for added stability. Clocking in at 12 kilograms excluding the power source and controller, the kinematic walker weighed roughly 56 times less than the Hardyman, lending itself more suitably to medical rehabilitation rather than industrial activities. A third modification added 3 piezo-ceramic force sensors into the sole of the exoskeletal feet to determine location and magnitude of the ground reaction force, which was then used to control the device with higher accuracy and improved response time. The final design incorporated DC motors instead of pneumatic actuation, and despite the limitations of the era's motor and battery technology, most notably their obnoxious sizes, this new actuation scheme still offered smoother motion and better tracking ability. Vukobratovic's consistent improvements created a solid understanding of the range of actuation methods available at the time and their related drawbacks. Despite this, it took 15 years for a new exoskeleton design to appear that could challenge the kinematic walker, and boy was it challenging. Jeff Moore of the Advanced Weapons Technology Group threw his tinfoil hat in the ring with the Pitman, a powered suit of armour for infantrymen. Housed in 500 pounds of fiberglass, ceramic and polymer composite armour, the Pitman was designed with 6 distinct layers. Starting from the innermost, layer 1 was made of impregnated antibacterial polypropylene, which, as wild as it sounds, PPE, or personal protective equipment, with internal antimicrobial weavings in the form of silver nanoparticles or copper oxide, are being studied for use in health services, so take from that what you will. Layer 2 was closed cell foam laced with heating and cooling tubing, the effectiveness of which is disputable to say the least. 3 is a sealed impermeable condom layer, assumably as some form of vacuum to limit heat transference to the external layers. 4 contains nitrogen-filled polyurethane bubble sensors, which were essentially bubble-wrapped displacement sensors to track positional compression and expansion of the suit. 5 was classic energy-absorbing closed cell foam, which exists today to dissipate kinetic energy, usually when transporting fragile materials. And finally, Layer 6 was composed of laminated composite armour capable of protecting the user from .5 caliber armour-piercing rounds, as well as, more stated, laser, thermal, nuclear, chemical and biological weapons. 9 years later, in 1994, the joint structure and kinematics were still unconceptualized, rendering it, like its designer, truly unhinged. The design's power supply system implemented auxiliary power units, batteries, and environmental control packs to maintain operator comfort, while magnetoencephalographic sensors, or MEGs, monitor brain activity, creating a phantom central nervous system to control the exoskeletal limbs. Despite the Department of Defense's consistent willingness to fund white men that read too much science fiction, even they saw the Pit Man as a pipe dream too complex for the current technology and refused to participate in its creation. Despite this, the US military continued to pursue exoskeletons elsewhere as part of the Warrior's Edge initiative, a comprehensive plan to modernize the soldier and maximize his capabilities. During the height of the Pit Man ravings in 1989, Mark Rossheim was only 1,231 miles away in Minneapolis, working on his vision for the exoskeletal future, which he called the... With 26 degrees of freedom excluding the hands, 500 pounds of load capacity, hydrostatically lubricated joints powered by ball screws and electronic negation of system weight through self-braking non-backdrivable joints, the Man amplifier was also never actually made. In contrast to the Hardy-Man's bulky and robotic designs, the Man amplifier more closely resembled the operator's joints, making the system inherently more user-friendly and stable. The mechanical joints were limited as to not extend past human limitations, and the battery-powered system reduced the system's weight, allowing for more dexterous and precise controls, lending it more naturally to disaster recovery, hazardous material management, and rugged terrain traversal. The operator would step backwards into the suit and load up, where pressure-sensitive cuffs feed signals to the actuator modules to initiate motion in accordance with operator movement, or they would if the device was ever produced. Don't worry though, because Rossheim was sure to write a book about exoskeletons entitled Robot Evolution, The Development of Anthrobotics, also published a book called Leonardo's Lost Robots in reference to Da Vinci, which, as irritating as Rossheim's unproduced designs are, I am desperate to read. Regardless, moving on to an actual, physical, real-life Here to carry us into the 21st century is Monty K. Reed. Growing up with learning disabilities, Reed was discouraged from attending university by his high school teachers. Feeling lost and unsure of his future, Reed was incorporated into the US military to jump out of airplanes. During one such event in 1986, Reed suffered a spinal cord injury and was told to accept his new fate of permanent quadriplegia. Unsatisfied with this prognosis, he began designing the life suit as a cure for his own ailments. As his designs grew in complexity, however, he became aware of the over 6 million people in the US alone who also lived with some form of paralysis, and through extrapolation, this could represent 2% of the entire world population. To this, Reed stated he quickly realized his mission was far greater than he could have ever imagined. A month after his accident, Reed experienced a miraculous recovery and no longer needed this technology for himself. Despite this, he continued to develop 24 prototypes between 1990 and 2014, each iteration an improvement on the last. The first life suit, LS-1, was the first exoskeleton Reed designed connected to a microcontroller, evolving through to LS-16, a CAD-designed rehabilitative therapy model with chassis, electronics and software all produced by specialist organizations individually. Reed continues to support the exoskeleton field with competitions, new prototypes and his life suit therapy clinics, providing rehabilitative technology and support to those in need. The life suit's development marked a shift in exoskeletal technology away from militarized suits of war and towards assistive and rehabilitative engineering to protect the lives of those suffering instead of Bleaks, $11 million. Oak Ridge Labs, $8.5 million, Millennium Jet, $5.1 million, Sarcos, $9.9 million, Arthur D. Little, $2 million, M. Aerospace, $1.7 million, MIT, I couldn't find the budget but it was probably very high. The US Defense Advanced Research Project Agency, or DARPA, began funding exoskeletal development yet again in 2001 with a new and improved budget of $50 million. $38.2 million of which was recorded to be spent funding exoskeleton development split between the aforementioned organisations, and the rest we can only assume went to a noble and trustworthy cause. Starting with Berkeley College, the Bleeks, or Berkeley Lower Extremity Exoskeleton, claims to be the first load-bearing and energetically autonomous exoskeleton. With 3 degrees of freedom at the hip, 1 at the knee and another 3 at the ankle, Bleeks provides the wearer with the ability to carry significant loads on their back over all terrains with minimal effort. With 2 powered anthropomorphic legs, a power supply and a backpack-like frame for payloads, Bleeks is said to be guided by human interaction, shadowing the operator's movement as they wear it. Weighing 48 times less than the Hardyman, but actually existing this time, Bleeks cannot crush golf balls, but fulfills Mosher's dream of tough terrain traversing technologies. Though Bleeks was promising in testing, it still faced concerns in its highly sensitive control scheme, static limb length, and unrealistic leg joints. Development moved away from Berkeley College to Lockheed Martin for further improvements, now known as the Human Universal Load Carrier, or HULC. Across the road in Salt Lake City, where the grass is green and the parks are fine, the Sarkos exoskeleton took greater inspiration from the Hardyman, a battery-powered, full-body exoskeleton that could amplify operator strength by up to 20 times, with user-selectable end effectors and redundant hardware for passive braking. Sarkos dubbed this device the Guardian XO, finally completed and presented in 2017, and employed in the military by January 2020. 74 years after General Electric began developing their cams. Only a year later, the Guardian XO Alpha unit was made commercially available, with beta units ready for testing in late 2022, bringing us to the 20 years in the making. The Guardian XO, though it has some pretty impressive stats, is not nearly the most prominent or impressive exoskeleton on the market as of mid-2022. That award is currently being fought over by a selection of corporations dominant in the market and a gaggle of newcomers vying for the throne. We won't be going over all of them here, but I'm going to show you a few of my favourites. Comment down below if you'd be interested in seeing some form of tier list or rating system of all these exoskeletons. Could be fun, could be boring. You decide. Starting off simple. The chairless chair is a chair sans chair. The lightweight exoskeleton snaps into place as its user bends their knees, distributing its weight such that the user is supported in a sitting position. It takes 30 seconds to put on and is advertised to maintain concentration and productivity, and reduce costs for days of absence. These have been employed in an increasing number of organisations across the automotive industry and beyond, and reveals the first hint of a red flag towards the ethical issues of exoskeletons, where robotic enhancements are advertised to the corporation instead of the worker, potentially promoting a less humanising view of one's employees, or refusing an employee the right to work without robotic enhancement. However, bugs. Upon further research, the Grasshopper does not allow its operator to jump approximately 20 times their body length in height. Instead, the Grasshopper is designed to address muscle and bone density loss in astronauts spending extended periods of time in zero gravity. Funded by NASA, the Grasshopper is a high-tech squat machine with an actuator in each knee joint, providing artificial, variable force feedback in zero Gs without the need for a spotter. From the highest of highs in space exploration to the deepest depths of the ocean, Dr. Phil Newton began his career by designing diving equipment in Western Canada. His equipment was so innovative that over the years he worked for commercial, scientific and military industries designing deep water diving equipment and technical diving techniques. Newton's most recent endeavour has been to build an underwater human settlement off the coast of Vancouver powered by Stirling engines with hydrothermal vent sources. Newton's second most recent endeavour was called the Exosuit, an ultra-lightweight, powered exoskeleton capable of operating safely at a depth of 1,000 feet. The ultra-lightweight suit weighs 600 pounds, reducible to 500 depending on the end effectors. But with 2 redundant oxygen systems and a high-density CO2 scrubber, the user has 50 hours of total breathing capacity while underwater. The suit has 4 1.6 horsepower thrusters, expandable to 8 upon request, and with gigabit Ethernet capability, high-definition cameras, and ImageNex 852 sonar, the suit is capable of transmitting everything it sees and more. air, sea and now land, Rewalk's Rewalker is a more down-to-earth exoskeleton, designed to be user-friendly and affordable to provide assisted rehabilitation for those living with spinal cord injuries. Battery-powered with motors at the hip and knee joints, the Rewalker senses changes in the operator's center of gravity, initiating movement in accordance with this shift, generating a sequence of assisted steps to mimic the operator's natural gait. This system is not without its restrictions though. The operator must be in general good health, with a weight lower than 100 kilograms, a height between 160 to 190 centimeters, healthy bone density and an unfractured skeleton. At this point it should be noted the difference in safety standards between industry and medical exoskeletons. Should the same restrictions be placed on exoskeletons in industrial use? Would this reduce working opportunities for those who exceed the weight or height limitations? Comment down below if you really think your opinion is worth something in this discussion, but really think about it. Really do take a second and... just take a look at this. Team Skeletronics is a group of award-winning inventors who create rideable robots. Based in Tokyo, their most recent design, Product 5 Skeletronics Arrive, is 9 feet 2 inches tall with a connected upper and lower body. Offering reduced burden on the wearer and suit-up time compared to the previous models, Skeletronics currently offers exhibition rentals with custom-designed exoskeletons on request, altering the frames, circuitry, lights and sounds to the user's specifications. Mirror technology is used to recreate the operator's movements, while more advanced mechatronics are used to control the fingers with a greater degree of precision. In public knowledge, these devices have never been used to stop crime or fight dinosaurs, but hope remains for the future of Skeletronics. Advertised as the world's first technology that improves, supports, enhances and regenerates the wearer's physical functions according to the wearer's intentions, Cyberdyne's wearable cyborg is a marvel of current exoskeleton technology. Designed primarily to improve physical function in welfare and medical fields, and has proven highly effective for heavy load lifting in the workplace. Most of Cyberdyne's commercial products monitor myoelectric signals to record the user's intent to control device movement. Via what I can only assume is some pretty advanced signal processing techniques, signal noise is all but eliminated, and the remaining electrical signals are translated to device movement. This may sound inaccurate, but combined with a series of learning algorithms that map intended movement to signal strength and location, the accuracy of movement reflection will increase with continued use. Cyberdyne has a variety of products, most notably their HALS, or Hybrid Assistive Limbs, designed for medical rehabilitation and well-being. The company was established in 2004 as a university venture to solve various social problems facing the aging society and continue to work on cybernetic systems focusing on medicine, welfare, life and the workplace. They even have a few less medical devices like the MBCL02 cleaning robot with elevator capabilities, the No Boundaries transportation robot, and the high-speed light pulse LED array light source that enables real-time photoacoustic imaging, or the Husleplalstertp, more commonly known as the Acoustic X. Speaking of high speeds, the global wearable exoskeleton market's compound growth between 2018 and 2028 is estimated to be 43.48%, hitting $5.4 billion by 2028. This growth being attributed to quick technological advancements and increasing demand from military, industrial and medical markets. The cost of both designing and developing exoskeletons remains high. Power units are bulky and limiting in their operation time, and with academic articles trailing far behind commercial development, it seems that it might take a little more technological development before exoskeletons are present in industry, healthcare and warfare to the extent that Mosher would have wanted. There are a whole host of social, legal, and ethical issues surrounding the integration of robotics into healthcare and the workplace, ranging from the dehumanization of workers to the perpetuation of an extreme class divide. So, if you want to hear about the potential dystopia these developments could plunge us into if not done properly, let me know down in the comments below. Thanks for watching, and try not to die before things get interesting.